All right, so I would prefer, of course, to be physically in Poland, but I guess this is the second best thing after that. So Poles keep telling me that there's never too early for vodka. So I'll start this talk with a little refresher. All right. So about me, like Ido has mentioned, I've been working in the industry for the last 15 years. I've started on the network security side. Then I moved to bot detection, which is more or less in the intersection between network and the web's security. I moved to JavaScript code protection, to client-side security, and I've been mostly focused on the website. I've been a speaker in a few conferences. These are a few of the ones I've been. I have several patents in application security, and my main interests are hacking the web, browser security, application security, reverse engineering, and heavy metal music. So for today, I'll be speaking about Magecart, which is a fairly new type of attack. Then I'll move to addressing web skimmers anatomy. The talk will progress by showing you how we are hunting down web skimmers with a few demos included. At the very end, I'll present you a Brutus Minus, which let's keep it a surprise for now. And at the very end, a little bit of Q&A. So about Magecart, assuming that you are not familiar with this type of attack, I'll just start by telling you how a Magecart attack goes. So it's a client-side browser-based attack where you have first-party code and you have third-party code. Third-party code is usually loaded dynamically from a third-party server. That code can load more code dynamically. You can have iframes, and those iframes can load extra code. So all of this code will end up in the same executing context, the browser, and we'll be able to fully view the DOM and all the other JavaScript code running in there. So what happens if one of these files is compromised? Maybe the servers were breached, maybe the attackers were able to penetrate the server and change the JavaScript in place. By doing that, they can inject arbitrary JavaScript code, and that JavaScript code will have access to everything, including form fields or paying forms. And that's what they do. They target payment forms and they exfiltrate the data that the user inserts in the payment form, namely the credit card information. So when one of these gets compromised, the whole environment, the whole browser and application, provided that it's running in the same execution context, gets compromised as well. So what happens next is the form gets hooked. We call this form jacking. It's another term for this type of attack. And the data is sent out to what we call the drop server. The drop server might sit in a unsuspicious domain name like coolestfonts.com, or it might leverage one of the existing third-party servers and domains, and that usually takes care of bypassing CSP and things like that are whitelisting the domains where the application can communicate with. So Magecart attacks, the name comes from it's probably coming from Magento, because the Magento e-commerce web stores were the first to be targeted, and the majority were Magento breaches. But nowadays, they can target any type of web server as long as it's serving JavaScript dynamically to e-commerce web shop. It's good enough for the attackers. They just have to find ways to breach those servers. It's also called a supply chain attack because it's going after the components of the web application, not served directly by the first party. And It all started back in 2015, more or less. A single group started it, but right now we have tens of different cyber criminal groups doing Magecart attacks with different MOs. The good thing about these attacks, at least for attackers, is that they scale very well. They only need to breach one server, modify the code, and they hit all the users at once. So if they stay 1 week in the server, they will be able to skim all the payments of that week of that website from all the users. They are also a good preference of the attackers because they seek the weakest link. So usually third parties are smaller companies, probably with less resources to dedicate to security. They are probably using ubiquitous software like Magento or other things. They are probably doing all sorts of mistakes in configuring those softwares, and that's how the attackers are able to easily breach them. So you might ask how often this happens. Right now, almost every week, certainly every month. I'm not going through all of these attacks, and that's the sort of thing that has been happening. So it's very profitable for attackers. So it's no wonder that they have been increasing. So talking about the anatomy of an attack, what you're seeing right now, it's the Inbenta's web skimmer. It has been used in the Ticketmaster breach back in 2018. You are just seeing the skimmer. It's a one-liner. It was concatenated at the end of a file. And as you can see, it's obfuscated, but this obfuscation is not really very resilient. By doing a bit of a manual deobfuscation, you get the gist of what's the code is doing. So basically, it's first checking if it's running in the right page, order, checkout, or one step. Then it iterates all form fields and known IDs, installs event listeners in on-click events, collects all form field values, replaces also the on-submit events, installs its own event listener, and eventually sends the scheme data to the drop server. And does it all again after 30 milliseconds. So it needs to keep running in order to give enough time for the user to enter the credit card data. So web skimmer kits are available on the dark web. So attackers don't need special skills. They can just buy a ready-to-use kit. These kits have loader code, skimmer code generation, and apply JavaScript obfuscation. They provide also a C2 admin panel like the one that you see on the right. They go roughly from $250 to $5,000. They are mostly used in spray and pray kind of attacks. So the users get access to breached third-party servers. They just install this, and basically they are attacking a lot of different web applications because the multiple applications are linking to the file that they had just modified. There's even a toolkit called Inter, which goes roughly around 1,300 and uses this special Caesar plus JavaScript obfuscation, which is also available on the dark web for $100. But the problem of this toolkit is that it does fake checkout pages. What this means is that the user is entering the data, but then clicks submit, and the transaction will not be successful. So this is actually a bad example because the user will realize that something has happened, will probably contact support, and probably the infection will be discovered sooner rather than later. So the best web skimmer kits, they try to be as stealthy as they can be. They will make sure that transactions are successful. while still skimming the credit card data. So now I'll present what we have been doing to hunt down skimmers. Before I get into the main theme of this talk, I will tell you about the solution and approach that we have been following lately. So we have built a tool, a client-side defense solution that it's basically able to alert and block malicious behavior. And it allows you to, for each resource in the page, regardless of being a first party or a third party, you set permission levels. So you can control whether a certain file can be loaded, should be loaded, or be blocked. You can control, if you allow it to load, you can then control high-level behavior assumptions about what it should be doing, and you can block it if they go outside your expectations. Things like should this file be touching any cookies? You can set those expectations, and the solution will be able to fence the scripts and block, and even block it from accessing cookies. And then at the third permission level, you can go as deep as you want in terms of specifying the behavior that you want to allow or to block. To give you a few examples, we can alert or block a script if we see it installing a specific listener, like on submit. Obviously, if you're using third-party code, you more or less know what it should be doing, if it should be touching forms, and you should have these expectations, and you can actually create rules to make sure that your expectations are met. We can block from sending data to unknown domains, or using a specific method like WebSockets, or if a file, JavaScript is touching a specific form like a payment form. Obviously, you shouldn't be including all your third-party JavaScripts in the checkout page, but some might be needed there for good reasons. But still, there's no reason why you shouldn't be limiting the ones that should be actually touching the payment form or installing listeners. So our solution will give you the tools to actually go deeper and enforce that. As you know, using conventional web technologies, you can do things like iframe sandboxing, but what you are able to limit inside an iframe, a sandbox iframe, is extremely limited. So you can either allow all JavaScript or disallow the JavaScript. You don't have fine-grained ways of controlling and enforcing specific behaviors that you want to allow and behaviors that you don't want to allow. So you can block JavaScript from adding elements to the DOM, so changing the interface, or using a specific API, or even to add more JavaScript dynamically using append child or insert before, for instance. So in general, what it allows you is to fence scripts, to create a cage around the scripts and enforce a least privilege principle applied to third-party code. And why not also apply to first-party code, because you can also be breached. First parties can be breached, and attackers can change the behavior of that code too. And not to forget, of course, if a third-party script is tempered and is actually able to execute on the execution environment, it's also able to tamper with first-party code and make it do something different. So everything should be fenced, and we should apply the least privilege principle to the whole web application. To do this, we use a technique called JavaScript Virtualization. I will tell you roughly how it works. So we need to add an embedded agent. This is actually JavaScript that you need to include in the page. It should be loaded as early as possible. And what it does is it proxies a bunch of things in the web APIs, like create element, insert before, XHR open and send. And when other files are loaded, they will actually see the proxied versions of those methods. And by going through our virtualized implementations, we are able to enforce the rules that were configured. So this is more than enough to mitigate this type of attacks, Magecart, from jacking, or any type of event handler hijacking. It's very useful to prevent data leakage, because you can enforce to what domains data can be sent out, and you can actually control what data is being sent out. So you can enforce the syntax of the data going out. And even our embedded agent code is protected with tamper-resistant JavaScript obfuscation. So in a nutshell, this is JavaScript virtualization. But what we have been doing lately, and the main topic of this talk, is Magecart classification. So obviously, by using the solution I've just described, we can fence the scripts, we can block data from going out. But we do that because we can roll out the rules to prevent those things from happening. But how can we know for sure that the thing causing that behavior was a skimmer in the first place? So this is a question that we had. And also, if it's indeed it's a skimmer, which skimmer are we talking about? So in order to solve this problem, we started building a Magecart classifier, and we started with a simple solution based in static code analysis. Little disclaimer here: this is a work in progress, so we have been working on this, and we'll keep working on this. And it answers the question, how likely is that this specific file contains a Magecart skimmer? And the answer is a percentage. So the requirements for this classifier are that it should be purely based on behavior. So we didn't want any hard-coded signatures or regexes, because they are very easy to bypass. You can change the aspect of JavaScript very easily by just applying code transformations, obfuscation, minification. So it's very easy to modify the aspect of the code just enough so that the signatures break. That's why we didn't want anything related to that. We wanted something based on behavior, because at the very end, the behavior of the code will be the same. It should also deal with obfuscation. Like I said, it should some code is obfuscated. Most skimmers are obfuscated, and since we are using static code analysis, we have to have a way to look underneath the obfuscation to be able to pick up the features that we are looking for. So the solution needs automatic deobfuscation in order to be effective. We also need to extract a very diverse set of behaviors, because right now we know what skimmers are doing, but we never know in the future. So we need to look for a very complete, a very diverse set of behaviors in order to better learn how they are evolving and to be very effective in finding them. And finally, it needs to be accurate. So when we say it's a web skimmer, it needs to be a web skimmer. Here you can see the architecture. Very simply put, we have an obfuscation detection module. It just tells us if it's obfuscated or not, and what obfuscation has been used, what tool. Then we have the obfuscator module that deobfuscates the code. Then we have a features extractor, and these features are passed to a scorer that comes out with the final score of the file. So we are using heuristics and simple heuristics, and we are grouping the features according to semantics and establishing weights for different groups. So right now, no AI has been used. I'm saying this now because otherwise I would get the question at the end. But we do have plans to use AI in the future, namely machine learning, to learn what features skimmers have been starting to do, starting to use, and to grow this classifier. These are some examples of the different features that we are collecting, organized in groups. So we're looking for very diverse types of things, obfuscation, of course, fingerprinting, if they're using hooking into events or forms, if they are using the network. So a lot of different things, even keywords. We're looking for certain keywords, usually used in payment forms like billing or credit card, etc. And we have been growing this list. So now time for a few demos. Let's start by the British Airways web skimmer. This skimmer, it's actually very simple. So you can see the whole skimmer on the right. It didn't use obfuscation, so it's very, and it was one of the first high-profile Magecart attacks that we have seen. And the problem happened when a dependency modernizer was tampered by someone, and someone at the British Airways has pulled a modified version of modernizer and deployed it locally. So this is one problem is dealing with third-party code. Sometimes a lot of people decide to host it themselves, but they have to be careful where they are pulling that code from, and make sure that you audit that third-party components frequently. So it's using target selectors, it's using event binding, and serializing the whole form and sending this using its XHR post to this domain Airways.com, which is not a domain that belongs to British Airways. This was actually the biggest GDPR fine ever. So some say that it lasted 15 days. Some say that it lasted 2 months. The official numbers say that almost 400,000 credit cards were schemed. And because they didn't have any protection mechanisms in place, they didn't took precautions. The British Airways was fined with roughly $230 million US. So it was the biggest fine ever of the GDPR. So here is the demo. To save time, I pre-recorded the demo in my laptop. So let me just hit play. So this is the modernizer library. And the code has been beautified because it was minified. And here at the very end, you see the web skimmer. And it's running in the onload events, actually using jQuery and binding the mouse up and touch end events and serializing the whole form and sending it to that endpoint controlled by the attacker. So we are running our classifier next. It's a CLI tool. We use as input the web skimmer file. And the output is the features that have been detected and the final score, which is 52%. So we consider over 50% to be the threshold that we consider to be a Magecart skimmer. So it's just over the threshold that we are considering. So we would still consider this to be Magecart, but not for much. So the detected features, so we detect a lot of different features, but this web skimmer is actually very, very different from the current web skimmer. So it doesn't use obfuscation. It's only a single function. So it's very different looking from the current web skimmers. Second example, the Inbenta that I had shown you before. So this example, this skimmer is quite different from the previous one. So it's obfuscated. It does page location check. So it's actually checking if it's running in the checkout page. The Ticketmaster web skimmer wasn't doing that, and basically it was running in all the pages. So that can be more noisy, because by running in all the pages, there are higher chances of being discovered. So by limiting to just 1 or 2 pages, they're actually being slightly more stealthy, and that's good for them, because the longer they stay in the page without being detected, better chances that they are collecting more credit card information. They're also using multi-page checkouts, so they're this is used because sometimes the checkout forms, they collect data across different pages. So they are storing data in cookies, and then in the final step, they pick up the data and send it to the drop server. So I'm going to run the demo in 3 versions of this file. So the first one is a deobfuscated version of this web skimmer. The second one is the obfuscated version of the skimmer, but just the skimmer, not the file where the skimmer was inserted. And finally, the third version is the obfuscated version, but within the scope of the full file. So I'm doing this because I want to provide a comparison between the scores of all 3 versions. So this is the deobfuscated version of the skimmer, and just the skimmer. The drop server is very easy to see. Let's run this. Okay, so the final score is 66%, and a few features are detected. Obfuscation is not detected because we deobfuscated the skimmer. We see like the use of regexes, keyword password, set timeout, location checking. Now, next we will run with the obfuscated version, but just the skimmer. And it gives us a final score of 81%. So certainly a good increase compared with the previous version. And obfuscation was detected. And finally, the full file and with the obfuscated skimmer. So, and now we see 85%. So as you can see, as we detect more features, the score gets higher, and we are more certain that we are dealing with the web skimmer. And even detecting one line of obfuscated JavaScript in a file that is not obfuscated is very suspicious, and something that weighs on the scoring heuristics. So as you can see, detected features, a lot of different features detected in the first version. It was deobfuscated, so it was easy to collect these features. The second version was obfuscated, but we were able to deobfuscate the file and grab the same features. We also detected the type of obfuscation. It was used the SunX tool, which is an open source obfuscation. It's not very good, but it's free, so it's used by a lot of bad guys. And finally, we detected the same things as before, but more than that, we detected that the obfuscation portion was just the bottom of the scripts. The final skimmer is this Caesar plus skimmer. This skimmer is basically, I brought this example because it's using the Caesar plus obfuscation. You can have a look at it in the image to the right. So the obfuscation is slightly weirder because it's using encoding. It uses multi-page checkouts, but not via cookies. It's using local storage. And it was hidden inside a jQuery plugin and ready to download by anyone looking for that type of functionality. So I'll actually demo this at the end when I'll talk about our deobfuscation for Caesar Plus. For now, I'm just saying that this particular skimmer was scored in 86%. So it's slightly higher than the last example. And the reason why is because the Caesar obfuscation is more unique. We don't see benign code using Caesar plus obfuscation that much. So it's when we see Caesar plus, it's very likely that this is some kind of malware. And together with all the other features that we have extracted, we concluded that that's good chances that we are talking about the web skimmer. So comparing all the skimmers that we have seen, I presented the samples in increasing scoring order. And as you can see, all of those samples were considered to be skimmers. One of the good things about this classification is, since it uses static code analysis, it's very easy to scale. So it's very easy to run this through thousands or even millions of files. We don't need to run a browser. We don't need to do dynamic analysis. So it's very cheap to run this classifier, and the results are very promising. So regarding the testing, we gathered a collection of 244 skimmer samples. We also collected all the JavaScript from the top 1,000 Alexa, and we pre-labeled all the skimmer samples. We ran the classifier through all the samples, including the skimmers, and at the end we compared the score that the tool gave with the label, if any, and we measured false positives and true positives and false negatives and true negatives. The results were very good. So we got 95% true positives. So we actually consider this to be very promising results. Obviously, we are still optimizing and improving the classifier, but for the first batch of results, I think they are very promising. So now I'll present Brutus Minus. This was the surprise I saved for last. So when working in this classifier, as you saw, we were finding a lot of different web skimmers using Caesar plus obfuscation. So we decided to build our own tool that deobfuscates Caesar plus, and I'll show you a very quick demo of that tool working on the sample. Before that, a brief context about Caesar plus obfuscation. as I mentioned before, it's available on the dark web for $100, so it's pretty affordable for an attacker, I would say. So no wonder that they are adding this type of protection techniques to their skimmers. It's actually more than this. Web skimmers are evolving a lot. They have been using things like bot detection or stenography. So it's a cat and mouse game for sure. So this particular obfuscation, it presents two layers of obfuscation that I will detail next. It uses different techniques to obfuscate strings and integers. For instance, they are converting a number to a string to the base 34 representation of that string. It's a way to encode the string. They are using ternary operators. They are encoding chars. They are using regexes to find and replace portions of strings. They are using dead code injection. And they are using things like unresolved symbols to break the code depending on certain checks. So the first layer is using a lot of encoding. As you could see here, this isn't valid JavaScript. What you're seeing there, it's a bunch of strings that need to be decoded using eval. And but it's just meant to hide what they are doing underneath. But it's more than that. It's actually doing anti-tampering in the second layer. So in the second layer, after decoding, it checks for a CRC. The CRC is included in the file in the first layer using a variable. And it's checking if after decoding, if the decoded matches the if the encoded code is matching the CRC, and if not, they're running they are calling an undeclared function to break the code on purpose. So it's actually slightly it's more difficult to automatically deobfuscate code that it's trying to self-check and trying to be tamper resistant compared with other obfuscations that are more passive, like the Sanex that you saw before. So here is a demo of us running Brutus minus. This is the obfuscated code. So most of the code is just the encoded strings. And here I'm running the Brutus minus, which is a CLI tool as well, on that sample, and redirecting to a new file. So here you can see the Brutus version of it. So as you can see, it's much more deobfuscated. We can still see a lot of different so we can see that code, but we see what matters. We see the page location check. We see it using local storage to do multi-page checkout. We see it sending data out, grabbing all the data from those form elements. And finally, we see the drop server address and the XHR posts to that address. So everything that we need in order to classify is here. And it's fully automated, the obfuscation. So again, the cost of running this is close to zero. So wrapping up, so we mostly addressed the topic of web skimmers. They are getting increasingly more sophisticated, as I mentioned before. They are using things like bot detection. They're using stenography. They are trying to use heavier obfuscation. And it will only get more complex as we go. So the defenses need to be sophisticated as well, but they need to be scalable and they need to be effective. So our approach is based on behavior, which is good because it's more resilient to the code changing form. So we needed a classifier to know what type of skimmer we are dealing with. So we decided to build one. That's what we presented. You can work with different layers of obfuscated code. As you saw, the results are very promising. If not deciding automatically, it can, at the very minimum, select the best candidates for analysis, and it scales very well. At the very end, as a bonus, we presented Brutus Minus, which is our Caesar plus the obfuscated. And of course, this will keep working on our classifier. So I don't know when will be the next talk, but we'll probably keep presenting the results as we develop this. That's all for me. Thank you, and back to the studio.